Hello everyone. In the beginning of the class, let us see new announcements. Okay, the first new announcement is May 25th, 2022. Class videos uploaded. Hello everyone. I have uploaded the class videos on May 25th, 2022 to YouTube. Their URLs are this, and this. Best regards, Wei Zhen. Okay, the second new announcement is the slides of Chapter 4 have been updated, version 2022-0530. Hello everyone. I have loaded the latest version of the slides of Chapter 4 to the eCourse2 website. The location and the file name are eCourse2 website, multiple input, multiple output techniques for wireless communications, course content, slides, Chapter 4, slides 2022-0530.pptx. Best regards, Wei Zhen. Okay, the third new announcement is the handout of Chapter 4 has been updated, version 2022-0530. Hello everyone, I have uploaded the latest version of the handout of Chapter 4 to the eCourse2 website. The location and the file name are eCourse2 website, multiple input, multiple output techniques for wireless communications, course content, handouts, Chapter 4, handout 2022-0530.pdf. Best regards, Wei Zhen. Okay, next let us look at the progress of the last class. In the last class, we have taught to Chapter 4 slides, page 131, BD. Okay, please open your slides of Chapter 4. Excuse me. Okay, and please turn to page 131. Okay, so this is a simple illustration showing how Doppler spread occurs. Okay, so finally the received spectrum has three impulses. The first impulse is at the frequency Fc minus Fd, where Fc is the carrier frequency and Fd is the Doppler shift. The second pulse is the second impulse is at frequency Fc, and the third impulse is at frequency Fc plus Fd. Okay, so you can see that the bandwidth of the received spectrum is BD. Okay, where BD means the Doppler spread. Okay. The simple example above was provided merely, that is only, to show, in principle, how relative motion in a channel can lead to a broadening of the spectrum. Okay, originally the transmitted spectrum has bandwidth 0. Okay, because the transmitted spectrum is only an impulse, and the received spectrum is broadened to BD. Okay, its bandwidth is equal to BD. This is obviously only one of many possible scenarios, however. Another type of geometry in which spectral broadening occurs is shown in figure 4.14. Okay, let us go to figure 4.14. Okay, figure 4.14 is the geometry associated with Clark's Doppler spread model. Okay, here is the transmitter, which is fixed, and the carrier frequency is Fc. And here is the receiver. Okay, the receiver moves to the right hand side at a speed v. Okay, and there are 8 scatterers, okay, named A, B, C, D, E, F, G, and H. Okay, in this figure, it is the transmitter that is fixed and the receiver that is moving. In addition, we assume that the receiver is surrounded by a circular ring of scatterers. Okay, so the receiver is surrounded by a circular ring of scatterers. Okay, totally 8 scatterers. And that there is no direct component between the transmitter and the receiver. So we can see that there is no direct component between the transmitter and the receiver. Please note that this dashed arrow is from the transmitter to the scatterer E, and this dashed arrow is from the scatterer E to the receiver. Okay, this is an idealized depiction of what happens when a vehicle is driving through an urban environment. Okay, so here the receiver is the vehicle and receives a signal from a cell tower. Okay, so the transmitter is the cell tower or the base station. After scattering from buildings and objects surrounding the receiver. Okay, so A, B, C, D, E, F, G, and H are buildings or objects surrounding the receiver. In the geometry shown in figure 4.14, the signal arrives at the receiver with many different frequencies. Okay, let us see figure 4.14 again. Okay, so in this figure, you can see that there are total 8 different scatters. Okay, so the electromagnetic wave arrives at the receiver with different frequencies. For example, energy scattered from scatterers A and E arrives at the receiver with frequencies equal to Fc plus Fd and Fc minus Fd respectively. Okay, because the receiver is moving toward the scatterer A, so the received frequency from scatterer A to the receiver will increase. Okay, so it is equal to Fc plus Fd. Okay, where Fc is the carrier frequency and Fd is the Doppler shift. Okay, and because the receiver is moving away from the scatterer E, okay, so the frequency that the receiver received, okay, from scatterer E decrease, okay, and is equal to Fc minus Fd. Okay, Fc minus Fd. On the other hand, energy from scatterers C and G arrives with frequency equal to Fc because the receiver is moving perpendicular to them. Okay, let us see figure 4.14 again. Because the direction of the movement of the receiver is this direction, and it is perpendicular to the segment C to G. Okay, so from C to G, when arriving at the receiver, the frequency is not changed. Okay, it is also Fc. Okay, for the geometry shown in figure 4.14, okay, let us go to figure 4.14 again. Okay, this figure. Okay, GANS reference 33. Okay, let us look at reference 33. Okay, reference 33 is a journal paper which was written by M.J. GANS. The title of the paper is A Power Spectral Theory of Propagation in the Mobile Radio Environment, which was published in the journal IEEE Transactions on Vehicular Technology in 1972. Okay, let us go back. Okay, reference GANS reference 33 has analyzed the power spectral density of the received signal as a function of frequency. In his analysis, he assumes that the arriving electromagnetic energy comes from all directions with equal amplitudes. The resulting spectrum is referred to as Clarke's model. Okay, so we can go to figure 4.14 again. So the energy from A, B, C, D, E, F, G, and H all have the same amplitude. Okay, so this is the Clarke's Doppler spread model. Okay, for the case of a vertical quarter wave whip antenna. Okay, what is a vertical quarter wave whip antenna? Let us see the handout. Okay, page 138. Okay, so page 138, problem 1. What is the vertical quarter wave whip antenna? Okay, solution. The vertical whip antenna is the most widely used omnidirectional antenna. Okay, we will explain what is an omnidirectional antenna later. Found in the military. The most common example of this type of antenna is the whip antenna used on vehicles and the ground plane antenna that is usually mounted on masts. Okay, we will explain what is a mast later, or other structures. The expedient. Okay, we will explain what is expedient later. Vertical quarter wave whip antenna, like the antenna shown in figure 11. Okay, let us see figure 11. Okay, figure 11 shows the vertical quarter wave whip antennas. Okay, like this. Okay, and this. Okay. So it's a single bare. We will explain what is bare later. Or insulated. Okay, we will also explain what is insulated later. Wire held vertically by a means of support and connected to the antenna connector on the face of the radio. Okay, so next, problem 2. What is the omnidirectional antenna? Solution. In radio communication, an omnidirectional antenna is a class of antenna which radiates equal radio power in all directions perpendicular to an axis. Okay, they are azimuthal directions. Okay, what is azimuthal? I will explain it later. With power varying with angle to the axis, elevation angle, declining to 0 on the axis. Figure 12 shows an example of an omnidirectional antenna. Okay, let us see figure 12. Okay. So, I need to make it smaller. Okay, good. So figure 12 is an example of omnidirectional antenna, a whip antenna. Okay, this one. On a walkie-talkie. Okay, this one. Okay, let us go back to figure 12. Okay. So problem 3, what is a mast? Solution. A tall metal pole used to support an aerial for radio, television, or mobile phone signals. Okay, problem 4, what is expedient? Solution. Helpful or useful in a particular situation, but sometimes not morally acceptable. Problem 5, what is bare? Solution. Without any clothes or not covered by anything. Problem 6, what is insulated? Okay, solution. Insulated is the past participle of insulate. Insulate is to cover and surround something with a material or substance in order to stop heat, sound, or electricity from escaping or entering. Okay. So next, problem 7. What is azimuthal? Okay, solution. Azimuthal is the adjective of azimuth. Azimuth is an arc of the horizon measured between a fixed point, such as true north, and the vertical circle passing through the center of an object, usually in astronomy and navigation clockwise, from the north point through 360 degrees. Please see figure 13. Okay, let us see figure 13. Okay, I need to make it smaller. Okay, so let me try 200%. Okay, good. So figure 13 is the illustration of azimuth. Okay, so number 1 is horizon. Okay, this one, horizon. Okay, and the number 2 is zenith. Okay, this point is zenith. And the number 3 is star. Okay, here. Number 4 is meridian. Okay, this one, meridian. And the number 5 is vertical circle. Okay, number 5. Okay, this one is the vertical circle. So number 6 is azimuth. Okay, this angle is azimuth. And the number 7 is observer. Okay, here. This point is number 7, observer. Okay. So let us go back to the slides. Okay, so for the case of a vertical quarter wave whip antenna, GANS shows that the received spectrum S of f has the following form. S of f is equal to 1.5 over pi fd times square root of 1 minus fc over fd squared. Okay, the equation number is in the wrong place. Okay, let me correct it. Okay, good. Okay, where fd is equal to v times fc over c is the maximum Doppler shift. V is the speed of the mobile, fc is the carrier frequency, and c is the speed of the light, which is approximately 3 times 10 to the power of 8 meters per second. Okay, figure 4.15 shows 3 example plots of the Doppler spectrum based on equation 4.34 for speeds equal to 20, 40, and 60 mph. Okay, here mph means miles per hour. Okay, where 1 mile is approximately 1.6 kilometers. Assuming a carrier frequency equal to 2.4 gigahertz. Okay, let us see figure 4.15. Okay, in figure 4.15, it is the Clark Doppler power spectrum for an unmodulated clockwise, CW carrier at 2.4 gigahertz. Here CW means continuous wave. So you can see that in this figure the x-axis is f minus fc in hertz from negative 250 hertz to 250 hertz. Okay, so the y-axis is the power spectral density from 0 to 0.025. There are 3 curves in this figure. The first curve is in dashed line, okay, which is for y is equal to 20 miles per hour, where y is the speed. Okay, this curve. Okay, the second curve is the dashed dotted line. Okay, which is for y being equal to 40 miles per hour. Okay, this curve. And the third curve is the solid line. Okay, which is for y being equal to 60 miles per hour. Okay, this one. Okay, good. Okay, so next let us see equation 4.34. Okay, this equation we have just seen this before. The U shape of these curves is characteristic of the Doppler spectrum. Okay, it is 25 minutes. Let us take a break.